yesterday, what we covered is the computational modeling of IB methods, and we saw some applications in thermofluids. So today I'm going to continue on these applications, and I'm also going to cover some fundamentals of flow-induced vibration. So that is the plan for next 1 hour. So again, acknowledgements to student contributors who have contributed to this this talk of the next 1 hour. And I'm going to present biolocomotion as the time permits, and that was done in collaboration with Professor Amit Agrawal and Atul Sharma, and funding was provided by DST and NRB. So again, I think I can skip the slides, but I'll just go if somebody has missed the yesterday's lecture. So we want to improve the heat transfer via FSI. So that idea is to use the vortices or secondary flow on our heated chips or devices, which can improve the heat transfer. And as we discussed yesterday, the mechanism was these vortices thin down this thermal boundary layer, which is at the surface, and which is not allowing to transfer the heat efficiently. So these volt flows can help to improve the heat transfer by thinning down or disrupting the thermal boundary layer. And we can also have some energy harvesting applications where these fluid dynamic forces on structures, flexible structures, impart some kinetic energy to a structure, and that kinetic energy converted to the electrical energy by the means of piezoelectricity or by the means of electromagnetic induction. So these are certain ideas we discussed. So let us discuss now directly to the thermal augmentation part. So here we are considering a D cylinder, and that is mounted on a spring, and there is a channel on which this cylinder, this setup is mounted, and this channel walls are heated. And what we are looking for is the improvement in this heat transfer on these walls. And then these cylinder, which when it starts moving by the virtue of flow induced vibration, it creates certain vortices, and these vortices spread out, and these vortices improve the heat transfer from these walls. So that is the idea, and this is the computational domain. As you see, our inlet velocity is non-dimensional 1, and the temperature 0 means it is an ambient, and the walls are heated. The non-dimensional temperature is 1. We actually solve spring mass system equations. As you can see, it's non-dimensional form here, and the Reynolds number actually is around 100, very low Reynolds number, but it still gives a good idea on the mechanism of the heat transfer. So we have done for this problem grid size independence and domain size independence. Here the domain is actually the channel length. I'm not presenting those results, but they are available in the paper which I cited in the previous slide. So this is a basic validation. When there is no body in the channel, you can have a graph of the Nusselt number as seen here, which is given in Bejan's book of the convective heat transfer. So we can see that our simulated results are very close to the analytical ones, and we are taking a very long channel, and you keep increasing the channel length, we start to get this value becoming plateau, which is getting just a constant value. And this is a constant wall temperature boundary condition, not the constant flux. Now let us look at some movies, and these movies are showing the vorticity and the isotherms and the Nusselt number plot. So this is something similar what I also presented yesterday in the last presentation. So if you see this is simple vortex shedding happening in the channel, and this is isotherms. And now, of course, you cannot see any change here, but again, if you have this cylinder motion, you start to see the change in isotherms as well. Now look at the Nusselt number where the plot is also not changing, but we hope it's to go to peaks once you start to have the motion. And now you may be wondering why we are considering a D section cylinder as compared to a circular cylinder, right? So that is something we will understand later, why D cylinder is efficient in undergoing very high amplitudes, and that is something phenomena called galloping. So we'll discuss this in the further slides. Now look at the circular cylinder. As you know of, it is a simple circular cylinder inside a channel, and again the vortex shedding is happening. Here the cylinder is mounted, by the way, on the spring. So you can see the vortices are moving, and but they're not actually reaching to the wall. And here you can see it is not able to disrupt the thermal boundary layer, as you can see. And the temperature or the Nusselt number for the temperature is not changing at all. So this is again similar condition, but the shape has changed. And although we are changing the shape, we are keeping the mass ratio, which is the mass of the cylinder by its displaced fluid, is constant, such that there are no inertia effects when we compare different shapes. This is the D section cylinder, and of course, here the reduced velocity is also important. So this is reduced velocity 8. And now if you see the D section, it starts to gallop, and we'll discuss what galloping is. And these vortices are spread out and creating a very different patterns as compared to the circular cylinder, which was just a Karman street. Here we have a vortex shedding, which is interacting with the heated wall. And now if I play the movie again, and you see how the thermal boundary layer is actually changing very close to the surface, and you can see this temperature contours there. And now you see the signal of Nusselt number at the wall. So I'm plotting at both walls, and you can see they are reaching peaks, but not at the same times. One is at the peak, other is at the bottom, which clearly shows the vortices are interacting here on the top wall, but not on the bottom. But in the next, just at the next moment, probably this will change, and this will be at low value, and the peak will be somewhere else. So again, it's a non-uniform improvement on a given wall, and that too is attributed again to the vortices which are being heated by this cylinder, which are created by this cylinder and being heated to the wall. All right. So now let us see further how we can understand it a bit more, and we can increase the reduced velocity. So probably, as you know, the reduced velocity is the ratio of time scale of solid to the fluid. So you can say whether you are either increasing the fluid speed or you are changing the spring stiffness. So now if you see the 12, you are 12, so you can see it moves even fast at larger magnitude, and then you can see the interaction is a bit stronger, and you can see it is all the way here to x is equal to 20. And see the peaks, and on the same scale they are much larger as compared to the previous case. Such high peaks are forming and very close to the cylinder as well as in the downstream. And the thermal boundary layer, you can see how disrupted it is, and these are the isotherms in this. So this is something interesting in the sense that reduced velocity also influences the heat transfer, and we can have a certain improvement. Okay. Now let us look at the characteristic of this D cylinder, and this is what I'm plotting is the maximum displacement or the amplitude of cylinder, and as a function of reduced velocity, as you can see here. And this reduced velocity, again, we have also done simulation for circular cylinder and also for D cylinder. Now let us look at circular cylinder. You actually have the same plot as you know of. It will go to upper branch, then lower, and then desync, as you can see here. But for the D cylinder, something special happens. So it is larger, the amplitude is larger, and then it further increases, and this something happens which is actually called as galloping. So galloping we're going to discuss in subsequent slides. And right now it is actually can be understood by the fact that as you increase the flow speed, the CLRMS or the force actually on the cylinder in this region increases. So there is no desync in the sense, and that there is a negative feedback from the fluid to the cylinder. So that is known as galloping. And here we see VIV and transition and galloping. We'll discuss these terms in more detail in further slides. But this slide actually shows a huge improvement in the amplitude of circular cylinder for the same reduced velocity, which is helping to cause more or stronger vortices, and they are spread out everywhere in the channel. And that's the reason we get a larger heat transfer. Now look at the variety of wake patterns which we get eventually when we vary the reduced velocity just for the D cylinder. So look at this picture. So 2S, as you know of, is the common street, two vortices. Then you can have a pair and a single vortex, which is called as P plus S. You can have two pairs, which mean four vortices, and that is something also there. And then 2P dash, we call it like a pair, actually two pairs, and then a single vortex. And then a variation of this is 2T, where you have three triplets, as you can see, 6 vortices in a cycle. So I'm counting vortices in a cycle. In a cycle, how many vortices I create in the downstream. Now there are 2T star, then 2T dash, and then 2T plus P. And why these vortices are so much in variety? Because of the interaction with the wall. So if you have a wall, it actually helps to create new vortices, and some vortices also coalesce. And this is something you can see here in this picture. So this is a typical 2S pattern. And you can see the circle marking a single vortex S. So S is we are just marking. Here you can see a pair plus S. So this is P plus S vortex. So you can see I am reducing the reduced velocity here. Right, UR3 is P plus S. And I'll just move this here. So this is only P, and then if you keep further going down, you can have a T. Like here, you can see this is a T, and then you can have 2T. So this is a function of reduced velocity. You can see I am changing reduced velocity from 2 to 20 all the way to the 20. Okay, and this bar is showing the displacement of these D cylinder. Now let us quantify the heat transfer improvement, and I'm just plotting Nusselt number as a function of distance. It is the same signal I showed you in the animation, but right now I'm just plotting it at different times in cycle. So you can see that a peak is here, and then as the cycle progresses, the peak changes. Here the changes are not so strong, which is UR8, but UR12, you can see that stronger peaks appear, much stronger peaks. And then you have also certain differences in top and the bottom wall, and that can be explained by the vortex dynamics of the cylinder and the heating of the preferential heating of the vortices to the top wall. Now let us compare different cases. So first of all, let us look at this plot. This is just channel flow. I am plotting the Nusselt mean. So this is now space average as well as time average. So Nusselt mean for the channel flow. This is for static D section cylinder where nothing is moving. This is circular D cylinder. It's not much difference between these two, but if you have D section cylinder, we have very large improvement. So comparing just these two where both cylinders are moving, you can see a large improvement in mean Nusselt number for the D section cylinder. So here Nusselt mean plot is with respect to UR, and this is definitely at a certain UR. I think it's UR12. So here you can see the Nusselt number first is smaller for low reduced velocity where the lock-in hasn't started, and then you start to increase, and there's a certain region where this is a lock-in region. It's basically improved, but on the top and bottom, it's not very different. And this is, by the way, for D section cylinder. And then now there is a slight drop and further increase in the case of top and bottom wall. And then you can see stays not increase and stays constant. Okay. And this is a plot of Nusselt peak. Peak is the peak value which we get in a cycle. So it can go very large reduced velocity. But what really matters is the mean value. And so we can actually argue that what kind of reduced velocity you will require to improve the heat transfer so that your efficiency can improve. Yesterday, we discussed about the pumping efficiency and efficiency of the heat transfer augmentation. All right. So moving on, I'll just now discuss more characteristic of galloping and flow induced vibration of cylinder. Before I move on, are there any questions? We can take questions in between if somebody has a question.
Sir, am I audible?
Yes, you are. Go ahead.
Sir, what are the effects of variation in Prandtl number.
Okay, so we haven't done that study. So yesterday we talked of some effects. So if you increase the Prandtl number, your heat transfer will improve because you can see the momentum diffusivity is increasing as compared to the thermal diffusivity. And this process, the vortices, the speed and the strength, that is actually very important. So in general, it will increase, but we haven't done the test to change the Prandtl number. So right now our Prandtl number, I think, is around 7, which is the representative of water. All right.
Yes.
So let us move on. Now let us consider several cylinders to just give an in-depth on what really happens once you change the shape of the cylinder. So we call it as front body and after body. So if you have a circular cylinder, its front body is what is in the front, and after body is what is in the after, right? After means downstream. So upstream, if you change the front body from this, let us say, to D section, so it forms a D, that's why we are calling it D section. And then if you further remove it, this part, it is inverted C. So you can see that D has become inverted C. Now, if you remove the, so here I'm actually changing the front body. Here I'm changing the after body. So if I just remove everything here, which is just this, so it becomes a C section looking like a C. And then if you just keep everything, it is D section, inverted D section, and then it's a circular section. So I can take a circular section and improve after bodies and front body, and there could be many more shapes possible, but these are just 2 more representative here and 2 more representative will give us a good idea on what is happening in FIV for these cylinders. Okay, so now look at all these movies. So I plotted this vorticity field. By the way, this is an open domain. This is not a channel. And now you can see how the vortices are being created for the cylinder. This green arrow here is actually representing the displacement of the cylinder. Now you see something special in D, as we have seen just before, and also in inverted C. You can see they are moving much wider, right? I mean, this arrow is much larger and vortices are very spread out. And these are clear signatures of galloping, as we will discussed. Now, what happens in D and inverted D and C are reduced amplitude, as you can see here. It's even in this case, especially C, is even lower than the circular cylinder. So clearly our after body and front body are affecting our flow induced vibration. And in this simulation, again, we are solving a spring mass system and we are keeping the mass ratio constant across the cylinder so that there is no effect of the mass ratio here. So that we can compare, say, apples and apples. Now let us look at the frequency response of circular cylinder. So there are a lot of data here. I'll just explain slightly slowly. So in first panel, I'm plotting the amplitude of the cylinder as a function of the reduced velocity. And what you see here is some acronyms, and these acronyms are the different type of branches we have in this response. So this is desynchronization, this is initial branch, this is upper branch, this is lower branch, and this is again desynchronization. This is a cylinder for circular cylinder, and this arrows what you see here on certain points are showing some kind of variation between cycle to cycle in a signal. So let us say you have some kind of beating in the signal, or the signal is not perfectly harmonic. So this cylinder is representing that amplitude variation for that particular case. Okay, as you can see, there are no variation present here because it's a locked-in branch, but here you have an initial excitation, so there are some variations here. Now, in the second panel, I'm plotting frequency contours. So any signal which I get for a particular simulation will give me a multiple frequency. If I do an FFT or discrete Fourier transform that signal, I'll get several frequencies. Normally, we are interested in the dominating frequency, but the fact is I get so many frequencies. I actually can plot all those frequencies, right? And I have so many values for that frequencies. Now I'm presenting those frequencies as a by virtue of the contours. Contours means Like if you have a very dark color, that is the dominant frequency. And the advantage of doing it, if there are some other frequency which is not dominant but is still present, can also appear itself as a contour. So this yellowish color is actually a contour. And that is done for several simulations, not just one. So if I just take a point here and go upwards in y-axis, I actually have contours of one case. Okay. And this is frequency response of the cylinder, right? And if I go for another case, I will get again a frequency contour. So for example, if I go here, this is a larger reduced velocity. You see a lot of frequencies is present here, and these are the two dominating ones, right? And here, if you go just here, you'll see one dominating frequency. So that is the frequency. And in this panel, the frequency is for the vortex shedding. So I'm taking the transverse force and just taking the FFT of that and then plotting the frequency contours. Okay. So this is two data sets I'm plotting. I'm also plotting so-called screw-hole frequency. So this is a frequency which a cylinder will exhibit if had it been stationary. So just a screw-hole law or vortex shedding screw-hole frequency I'm plotting. It will appear itself as a straight line, as you can see here. I'm also plotting another red signal, SPM, which is for screw-hole frequency modified, which we'll discuss in the next slide. But right now, you just keep in mind, I'm also plotting together with this. Now, what do we see here in this response? And you can see probably if you are working in VIV, this may be just a like a very preliminary for you. So cylinder is not oscillating at all initially, but then it starts to vibrate and go to a larger amplitude in the initial branch, and then hit it another branch where the amplitude is higher. So in literature, so far, people haven't talked of upper branch and lower branch in that low Reynolds number. Only they are talking in high Reynolds number regime. And in fact, there is a good difference in upper and lower branch in the high Reynolds. But here we are trying to characterize it for the low Reynolds number, and that is based on the phase. So here in this nonlinear dynamics problem, we also have a phase between the displacement and the forcing. And that phase could be of two types. One is the total force, which I have on the cylinder, and then I could also have just the vortex force, and that could have a difference phase. So the characterization here is if the phase, total phase is 0, and the phase of the vortex force transitions from 0 to pi, it's an upper branch. And if the lower branch is there, then total phase transition from 0 to pi, and the phase of vortex force is pi. So these two we use to demarcate this. So you definitely argue where this line is coming from. So this line is based on this criteria, and we have also plotted phase. I'm not showing it here. Now, cylinder is showing a typical response, a lock-in region, and then a desync, and then initial excitation. Now, if you look at the frequency, it is non-dimensionalized with respect to its natural frequency of the cylinder, and you can see the value is almost 1. So this streak is actually streak line kind of behavior is showing its lock to its natural frequency, and this is a typical characteristic of a lock-in regime. And in the vortex shedding frequency, you can see there is a third harmonic present because this is around 3, and this is also appear in the signal, and that has also been explained by the fact that we have a symmetric vortex shedding. So after lock-in region, the cylinder desyncs and its frequency is close to again to the screw-hole frequency, as you can see here. So in a way, the frequency of vortex shedding gets modified and it locks in to the cylinder natural frequency, and amplitude is larger. So this is a roughly idea of a circular cylinder. And now look at the D section, which is even more complicated and exhibits several regimes as compared to the D section. So let us discuss first what happens initially, desynchronization. Then you have an initial branch, and briefly then you have a lock-in. So lock-in, again, our same definitions. You can see a larger amplitude, and there are no fluctuations in the signals, as you can see. And then our frequency is also close to its natural frequency. And so this is the effect of this is the definition of lock-in. And now something odd happens. These frequencies start to show multiple frequencies right after locking. And you can see the amplitude is keep increasing. Ideally, it should desync had it been a circular cylinder, but it does not desync. And then what really happens is, in the case of dissection, I will explain here. What happens is, if you have a cylinder which is actually a flat facing, it basically starts to feel more force as it moves at larger amplitudes. So this is an apparent increase of the fluid force or the flow velocity when the cylinder is moving. So you can think of a basic concept of relative velocity. If a circular cylinder is there, if it is moving, it will not feel an extra force because it's so symmetric on top and bottom. But if there is a flat surface, you can actually see that at larger velocity, if it moves with a very larger velocity, it starts to feel a certain extra velocity just because its own motion. You can see this is an extra velocity, and this force will be felt also at certain angle to it. And that is only a characteristic of the cylinders which are actually flat facing. As you can see here, you can see this, because of flat facing, this extra apparent forcing is there. Had it been a symmetric one about this x-axis, then this will cancel out and it will not feel that extra force. And this is actually providing a negative feedback. The faster it moves, the more forcing it feels. This is not the case in the case of circular cylinder. And that is what it is called as galloping. And it starts to gallop means it starts to vibrate even more vigorously, and the amplitudes keep increasing, as you can see here in this signal. Now, once it starts to gallop and starts to have fluctuations in some amplitude and also these frequencies, we can see what are its dominating frequencies. So dominating frequency, ideally, it should be close to the fluid flow frequency, which is this curve. But what we are seeing, the frequency is actually closer to another frequency, which is modified. Now, based on this movement, which is moving faster, we also can modify its Strohal frequency, which means that had it been stationary, it will feel more forcing and the Strohal frequency. So what we did simulations of the stationary cylinders. So several stationary cylinders and different alphas or different configurations, and we plot it here. And this has been already done long time ago, 1932, in Den Hartog criteria. If the change in the transfer force with respect to alpha is actually positive, then you start to have a galloping, which is the characteristic of these cylinders, which normally have this flat facing, like a square cylinder and this D-section cylinder. So using this data, we can figure out its modified Strohal frequency, and that we can actually figure out, because of the increased apparent force, what is that modified natural frequency. And that we can plot here on this frequency. So blue is the showing when it is stationary and we are increasing the flow velocity or reduced velocity. What is the change in the vortex shedding frequency? It's just linear. But once you have that increase by the apparent forcing, you start to have a slightly different curve, which is slightly larger than the this Strohal frequency. Now, surprisingly, this red curve agrees with what we get in simulations. I mean, the simulations which account for the motion. So red is the simulation based on simulations, but the stationary ones. But here the contours ones are where the cylinder is actually moving. So showing that this red signal, the dotted red, is matching with the dominant frequency, is actually showing that the cylinder motion in galloping is locking to its modified natural frequency, not the previous Strohal frequency. Actually, it's Strohal modified Strohal frequency. Now you can see certain things here. The dominant frequency keep increasing. It is close to the red curve. And then what really happens, at some point, all of the frequencies which is appearing in our forcing signal, basically they lock again. They come closer again. As you can see here, this is the harmonic of the third harmonic of the natural frequency. This is the dominant one, the modified natural, and they lock again. And why that locking happened? The locking is happening because this red curve is going to intersect this dominant frequency and this other frequency. And you can see everything, all other kind of harmonics disappear, only few remains. And this is a clear lock-in again. And once we check the phase characteristic of these first lock-in and second lock-in, they basically agree for the lower branch for the circular cylinder. So they clearly L1 and L2 are the lock-in like behavior of this D section. While GD is the galloping, where we see it close with the Struhal modified Struhal natural frequency. Okay, and if we keep going further, you can see it again goes to galloping, and again the dominant frequency here is very close to the modified natural frequency, and it's away from the Struhal frequency. And you can see here again, because it is going to intersect with the harmonic of the natural frequency, again it goes to lock-in L3 and then galloping. So this is something which we have not seen in literature, how the several frequencies are there and they lock and they disappear, the harmonics disappear, and then again galloping occurs. And that too we have explained with the modified naturals, because somebody can definitely argue what are these frequency, they are not really matching even with the Struhal frequency or other frequency. So the explanation is actually the Struhal frequency also get modified in the event of a large motion of the D section cylinder. Okay, so I'll summarize this this whole simulations. I'm not showing a lot of data is there on the C section, D section, inverted D. And there's a lot of discussions on phase characteristics and all other characteristics. But this is the summary of this paper or this study. And what you see here, the plot with respect to reduced velocity and the plot is for the amplitude or the maximum displacement. The different cylinders are showing different behaviors, and the symbol actually is the cylinder shape, as you see. The circular one, of course, is this behavior, and this red and blue representing the upper and the lower branches based on the criteria. So this is the circular cylinder typical response. And now if you see the C section, you can see there is not even a lock-in present here. And then the inverted D, it locks for a very brief period, but even shrunken. So these two things, these two cases show that if you have a decreasing after body, which is this case, you have a VIV suppression, tendency of suppression of VIV. So you can see from cylinder to D to C, inverted D, cylinder to inverted D to C is a VIV suppression, and that too we see in here signals. Now inverted D and D and inverted C were the most interesting, because they exhibit very rich physics of FIV and different regimes, and here had been characterized here a little bit simplicity we have chosen, because we are just showing the upper branch and then the galloping branch like this, although we have certain characterization as I discussed. And you can see that in fact C section is even galloping for a very large values of amplitude, and the fluid mechanics is also very interesting in the sense that if I go back to show you the fluid mechanics of the inverted C, you can see there is a fluid mechanics here in the cavity of C, which actually impacts its motion. So you can see here how this cavity is getting filled and then it is getting drained, and it is actually impacting its amplitude. So inverted C itself is interesting, although the characteristics are very similar to D, but it also helps to have such kind of shape which even go for a larger amplitude. For example, in the applications of energy harvesting. So this is something also a finding that if you decrease the front body, you have a stronger VIV galloping kind of regime as compared to the other cases where you decrease the after body. Now we have also done energy harvesting potential, and we have plotted energy for different shapes and compare the efficiencies. What is the probable efficiency? So what we see, the efficiency of D section is not very high, although the power generated is very large because its amplitude is large, as you can see here. But it is broadband response, which means that the energy can be extracted for a wide range of velocity because it goes for galloping and it is not desynchronizing. Although the circular cylinder is showing a larger efficiency, but it is desyncing very quickly. Now let us look at another interesting problem which we did recently. It is actually under review with a journal, but here we are getting very similar responses of VIV, but not exactly the same. And it's more interesting than probably a circular cylinder linear VIV. So this is a flow-induced rotational vibrations of an inverted rigid cylinder plate. So we have a torsional spring, and there is a cylinder which is fixed with a plate. Everything is rigid here. So because of this torsional motion, the plates can go to angular motions, as you can see here. And it is a typical big domain, and we are using our IB method as discussed yesterday. And you can see mass ratio, I think we have kept it 10 and throughout this study. And what we see very different regimes as we will see. Now, what was the background to doing this is there's so much literature on the inverted flags or inverted flexible plates. And the idea here is to kind of use this problem for understanding the dynamics and also applying this for energy harvesting. And what we wanted to say that, okay, of course, you can do this problem computationally, but it may be very computationally expensive. So we can develop a simpler model for this flexible plate problem, and we can understand the dynamics from that point of view. And this type of configuration like this flow induced may be also easy to manufacture and maybe easier to install. So these were the ideas when we started this problem. And now we did first a code verification. So we introduced the rotational motion, right, first, and also heaving or the linear motion we already have. So we tested the code for a coupled pitching and heaving of a foil, which is already there in the literature. And these are the displacement, pitching displacements. And so this is going pitching and heaving, which means the linear and angular motion simultaneously. So you can see again a pitching motion here, and then desync here, and then this is angular motion. So after verifying the code, we went to understand the linear dynamics, the fluid dynamics or the FIV of the system. And it's very interesting in the sense we get to recover several regimes. So let us see one by one. One is this initial excitation. The plate is barely moving, although there is a vortex shedding in the downstream, as you can see. Here you have so-called intermediate symmetry breaking. The plate kind of breaks symmetry slightly away from its mean position. Now it's vibrating, but not at its mean position, right? And you can see slight change in vortex shedding. Now what we discover also, which is called as chaos. So you can see the plate is just vibrating without any harmonic frequency, or so it's vibrating randomly. We'll discuss more about that later. And that is, we are calling it as a first chaos. And then later on, again, it breaks the symmetry and it's reached all the way here. And then the vortex shedding, of course, it is happening. There's slight vibrations there. And then there is a lock-in region. You can see the huge amplitude there. And then the effect on the vortex shedding. And we can see these spread out vortices are reminding us of our D cylinder as we had. And then there is a chaos where there is no definite motion, and which is with a larger amplitude, not the smaller one, which was the first one. Okay. So now let us see this data in plots, and we will discuss why we are getting these regimes and how we can use these regimes for the understanding of dynamics and also from the point of view of energy harvest. So this is the signals of different cases, and I think if I put it here, so you can see I am changing from top to bottom is reduced velocity, and the previous regimes are also functions of reduced velocity, which I showed you. In each row, I am plotting the coefficient of movement. Here, it will not be the lift or transverse force. It will be the movement, which we are plotting as a function of time. This is the theta, which is from its mean position. And this is the phase portrait, as you can see, is a function of plotting as a function of theta and theta dot. Theta dot is its velocity. So here, this is initial excitation, nothing is happening. You can see the thetas are very small. And then slight variations, in thetas. And then further, you can see this signals become very random. So when signals become very random, there is a theory of chaos where people calculate so-called Lyapunov exponent. It is actually given in detail in these papers and these books. And lambda characterizes the chaos. Lambda, if it is higher, the chaos is definitely there. For very small lambdas, there is no chaos. So now you can see the lambda for this signal and this signal is higher. And you can see there is no definite motion here. It's all the way here. Right. And now these signals also have been changed, as you can see. And now further, if you see, we have a clear signal which is at UR 8.5. This is a characterization of lock-in. And then further again, it is going random. Although there is some kind of pattern there and this lambda, but it's very high. So again, it's fall in the chaos. And then further symmetry breaking, where you have very low lambdas, very low lambda, yes, and then very low thetas as well. Actually, you can see. So these signals actually corresponds to these ones, the first chaos and second chaos. We can see the lambdas are very high, intermediate symmetry breaking, and the lock-in, and the final symmetry breaking. So let us see further in details how we can understand it in even better. Here is the plot of theta versus reduced velocity. Now, theta is very low, and these 1, 2, 3, 4, 5, 6 are different regimes, as I discussed in the previous slide. So one is initial excitation, and if you go back to second is intermediate symmetry breaking, as you can see here. And then after that, the third is first chaos. And then fourth is, if you see, another symmetry breaking. Actually, fourth is lock-in, and then fifth is second chaos, and sixth is final symmetry breaking. So order actually is this. So let us go by the order. First, initial excitation, then symmetry breaking, then chaos, then lock-in like behavior, then chaos, and then final symmetry breaking. So that is the order. Now, chaos can be identified also with several frequencies. So these are the same frequency contours I have shown you before. I mean, the way we have plotted, I've explained you before. So you can see a lot of color here, which means a lot of frequencies. And then this is a clear signal for chaos. And of course, we have calculated the Lyapunov exponent, which is showing the behavior is essentially like chaos. Now, in lock-in, we are getting a single frequency that is expected, and we are also getting a larger amplitude that is also expected. But one thing was not expected is this frequency actually is not very close to his Strohal frequency, right? Because we have seen that is actually closer. That is one characteristic. So now what we also see, this frequency is when after it's desyncs, you can see it's slightly aligned with the Strohal frequency, and there is a harmonic present here in this signal. And now if you see, we are also plotting this theta mean. So this is a mean position. Now a mean position is slightly deviated here if you see in the second regime, which is the first symmetry breaking, and then all the way is very small, which means it's oscillating about its mean position. But when the symmetry breaking happens in the last regime, you have a very large theta bar, which means that a final symmetry breaking. Now, how to understand this is first we plotted this chaos regime, and I'm just plotting data of several simulations, which actually is showing different initial conditions for these simulations. So I'm displacing this plate displacement initially by some values. These values are written here, and they're very small. So what we can see here that all the simulations which started with slightly different values end up in a very different later stage. So these dots are the trajectories or the phase portraits of those. And you can see how they started at the same point, but actually ending up very differently. and some are on other cycle, some are on other cycle. So this is something also have been explained in literature called Lorentz attractor or butterfly effect, if you have heard of. So essentially, the minor change in the initial condition actually can affect the final outcome, and there is no guarantee that how it will behave. There is a no prediction, or there is no prediction of the final limiting cycle. So this is something also a characteristic of chaos, which we have also seen in our simulations, and that something agrees with our previous regime reduced velocity 9.1. As you can see, if you go back, it is basically this cycle where it is showing a strange attractor or butterfly effect kind of thing. And if you go back, this is this second chaos, which we just saw. Okay, now after this, we have done a model which is able to explain these numerical results. So this is a theoretical model. This is called as quasi-steady aeroelastic model. So what this model says that you have a torsional spring equation, right? This is the torsional spring you can see in non-dimensional form, where alpha is its displacement, the plate displacement. Now this forcing from the fluid, let us say it is Cm, coefficient of movement, can be expanded using Taylor series. And then once you expand that in Taylor series, this whole term, which is showing the Cm at any given alpha naught, and the change in that Cm with respect to that alpha naught multiplied by alpha, can be said as Kf, which is called as added stiffness. And this whole thing can be put on this side. So we can write it that in a compact form like this. So this is the equation which we have, which will govern this system, because the fluid effect is considered as an added stiffness into the system. So this is an added stiffness Kf into the system. And now we can use this theory to explain what regimes we are getting. So first of all, if we can have a critical alpha CR based on this value, if it goes to 0, and then we can define when the instability is creeping in or when the instability is setting in. So based on that Kf value, we can figure out. So we use this to put as 0 first, and then we use this Kf value and we get this equation. So now if you see, we have a critical Cm, which is a function of alpha CR, and this is a plot of the forcing and that critical value. Yeah. And then we have some constant here, which is representing the slope of this line. So what we did several simulations, but not for the moving body, but for the stationary body. So we kind of change the position of this plate. And then what we want to plot is how the Cm varies with alpha. So the Cm actually varies something like this. So Cm variation is this. So these are the simulation. Blue curve is based on the stationary plate simulations, right? It kind of represents how Cm varies. And then now using this theory, we can plot a line, which is this red line, which shows that when this line will intersect this curve, this Cm, we can have several kind of situations, like a trivial solution. We can have more solutions, 3 solutions, or we can have something like this. So these 3 regimes, which are in general, we are getting chaos where there is actually no solution or any solution, or symmetry breaking, or a 0 mean position, which includes IB and also lock-in. So based on the intersection of these 2 lines. So if you see in chaos, this slope is actually very close to this initial slope of Cm. So in a way, it can kind of intersect anywhere where you are in this regime. It's very sensitive to this this intersection or in this region. That's why we are getting chaos in between. And then after that, you have these solutions, which can either lock these 2 points or these 2 points. So that's why you have a symmetry breaking. So it can break into symmetry because of this region. And when you have a 0 mean position, you will always have a solution, which means that it's a definite solution. So this is a 0 mean position. So this theory actually explains first why we are getting chaos and why we are breaking the symmetry. and what kind of critical values are required once you do not have the chaos or once you have a locking. So in order to further prove that, we plotted a so-called bifurcation diagram. So we plotted this alpha CR from the theory, and also we plotted theta dot zero, which is the zero velocity points from our simulations, FIV simulations. And then we are also plotting mean absolute value of from the simulations, which means that a positive amplitude mean value of the simulation. So what we see that the chaos is characterized by a lot of blue points, which means it can go anywhere. And then you have a limiting cycle, as you can see here for the locking case, right? And then you have a onset of symmetry breaking, which agrees with our theory. So this is actually symmetry breaking. So you can see all the blue points can come here. So and then we have a certain chaos in between as well, which is well predicted by the theory also. So this pitchfork bifurcation allows us to explain the regimes as we are getting them. And now with the current model, we can modify the frequency what we have, the frequency what we get from the model, the theoretical model, and plot them with simulation data. So what we saw that this frequency which was dominating in lock-in is actually agrees with that model. So that explains why it is not very close to the natural or the natural frequency, which is modified by the stiffness of the system. So this is actually a natural frequency of the system modified by its stiffness, fluid stiffness. Okay, now we explain several things about the regimes, about why we are getting different regimes in between, and also the characterization of this frequency. And we also plot the modified STM, which was proposed earlier in our dissection paper. And what we see, surprisingly, that modified STM is actually agreeing with this velocity response in this symmetry breaking region, as you can see here. So with that, we can explain several things, and this problem can be also used for energy harvesting, as we have done, several people have done earlier, to use inverted flags as the energy harvesting potential. So here we can have some estimates, and then we can plot the power, and we can also compare with this VIV of circular cylinder and what is the power we are getting. So we are still working on it to understand the efficiency part, but power is slightly higher, although it was done at slightly larger Reynolds number for this case. So so this problem is very rich in its FIV regimes and the nonlinear dynamics, which we have explained with the help of a theoretical model and stationary body simulations. Now, finally, if you see, these are the regimes we get. If we plot pictorially, this is initial desync, this is symmetry breaking, this is first chaos, this is locking. So this is actual data gotten from simulation. It is not a schematic. This is second chaos, and this is the final symmetry breaking. This envelope is showing the extent of your displacement, angular displacement. And what you get in this inverted flag, this is state mode. This is taken from literature. This is flapping mode. This is deflecting mode, as you can see. And again, in the another study, this initial excitation, then again, this locking kind of behavior, and then this deflected mode. So by and large, our regimes also matching with another complex problem of flexible flag, and our theory and the simulations can be used actually to explain those easily. There's something also more questions like people have done simulations with the rigid flag without a cylinder, where they get slightly different regimes. So it's still working on it, but I believe that we can also explain why the cylinder helps actually to reduce chaos. In this case, they actually get more chaos, and we are still working on that. Now, if I think I have some few minutes, so I'll just quickly explain my last problem, and then probably I can end my presentations. So we also did simulations for a flexible plate, but it is mounted vertically or cross flow configuration, and we are looking at its FIV regimes. So we are characterizing it angular motion, as you can see, and then what are the contribution of different modes, and how these mode interplay happens as we change the reduced velocity. So here the parameters are non-dimensional elasticity, mass ratio, reduced velocity, and we also account for the modified natural frequency due to added mass and curvature induced stiffness. So there are different regimes, as you see. We did several simulations: high elasticity, low elasticity, and then high mass ratio and low mass ratio. Of course, we're going to put all together in terms of the reduced velocity, but you can clearly see here the plate is barely deforming. Here the plate starts to show some nodes, which means it's a second mode lock-in. And this is again high mass ratio with a second mode lock-in, and this is a lower mass, the first mode lock. So different regimes we are getting. Of course, the vortex shedding is not very complicated. It is on the similar lines as we have for a bluff body, but what is interesting here is these regimes we are getting. So here are the data from the simulations. This is superimposed image from the simulations of the plate. So this is first mode locking. This is desync after the first mode. And if you keep reducing it, again, it goes to the second mode locking and then desync. So here the difference with respect to previous problem is you can have multi-mode locking as you are increasing the reduced velocity. And then same for the mass ratio. So I put all this data together in terms of the reduced velocity. So you can see these peaks are showing the lock-ins of first and second mode. And then this red curve is showing the energy exchange between the fluid and solid, which is on the similar lines. If you have a lock-in, you have a larger energy exchange. And then this is the frequency plot, which is again on the similar lines, that the frequency locks, the fluid frequency locks to the natural mode of the plate, and then you can see how it aligns in this case of second lock-in. And we also plot the modal contributions, which is showing the evidence of where the first mode lock-in and the second mode lock-in is there, as you can see in this plot. We have also done some preliminary analysis, like if we want to use this system for energy harvesting. So we calculated strain energy density, which is a good parameter to have a deformation on a piezoelectric patch if you want to have. And then you can calculate the strain energy density, cumulative strain energy density across the height of this plate. So as you can see here, the strain energy in most of the cases is higher at the very base where it is attached or fixed. Now we have plotted this strain energy density and figured out that you just have to attach a 20% height piezoelectric patch. So this is lines are showing like 80% kind of energy recovered if you will attach. So you can actually optimize the cost of the piezo versus the energy. So if you attach a piezo which is as good as the length of this plate, probably you have to spend some money or the cost for that piezo. But on the other hand, if you use a smaller piezo, you can get actually similar amount of energy with spending lesser cost. Okay, so I think I'll stop here because I am out of time. The biolocomotion part actually can be covered in the evening. So maybe I can take questions now if you guys have.
Thank you, Professor Rajneesh, for this excellent seminar.
Yeah.
Lots of new and interesting results we have seen. So, from the audience, if there are any questions, please ask. Yes.
Sir, for energy harvesting, which is greater system, it's chaotic or non-chaotic?
Of course, we want non-chaotic, because chaotic, you don't know which direction it will go. So we want a case where it is locked in to a certain frequency and we have some idea, okay, how it's going to behave. So non-chaotic system is definitely preferred.
So sir, during active, when we are, for example, if we are proposing for certain active control approach to control the chaos of that system. So what are the different ways to control that?
Can you say it again? I did not get the question completely.
Sir, means if we have some precursor, means that the certain system is going into chaos.
Right.
So how can one control that basically without reducing, like without manipulating the UR?
Okay. So I think once we have this knowledge of different regimes, let us say you have certain region in which chaos is there. So you can actually change the parameters such that whatever available wind speed is and whatever available material parameters is, that you do not hit the chaotic regime in that response. So the simulation can help you to design that system that it does not go to chaos, and it most likely should go to lock-in as soon as possible. So in general, the velocity available, let us say the wind energy may not be uniformly available. It is varying during the day and night, right? And also in different seasons. So you can do a stock of things like, okay, what is wind energy available and what material parameters I'm choosing. So based on that, you can decide actually. But I think the idea is to target the lock-in region so that you can maximize the energy harvesting.
Two more questions?
Yeah.
Sir, in the first part of your work, sir, I have seen for the discussion, I have seen the amplitude function you start from. Then I have seen the transition and developing section here. So how the section are different? Because I have seen the continuous part.
Again, I am not able to get the question. Can you just maybe go close to mic or?
Yes, yes. You come here, come here.
Yeah, you can come close to the computer. That would be good.
You come here.
Sir, in your first part of work, sir, I have seen the amplitude process based Sarkar.
100%?
Amplitude process based Sarkar I have seen for the D-section cylinder. There I have seen the continuous curve for the transition and for the transition regime and galloping regime.
Okay.
So how transition regime is different with the galloping regime?
How? Which regime? Transient.
Transition regime is different from the galloping.
Okay, I get your point. Okay, I got the question now. So basically the question is like how transition is different from the galloping. So anyway, it is actually one regime is changing to another. So there may be some place where you do not have a definite way to say which regime it is. So maybe just by just some ad hoc way, we can say, oh, this is the transition regime. So we do not have any specific criteria for that transition regime I mentioned actually. So, yeah.
In galloping regime, you are referring that body is following some modified stroke natural frequency. So what are you referring to that? What is modified stroke?
Okay, so I think this is a good question. So basically galloping, its very nature is it is feeling more force and it moving very fast. So if you have a body and you are moving it very fast, right, it is feeling an apparent force. So I will give you an example. So if you have a drag force on a car which you are driving, normally you expect if you drive fast, you have a linear increase in the force, but it's actually non-linear, right? So it scales as v square. So the forcing is changing with the speed of the car. So here, if I think in my system also, if I'm moving faster, I am feeling more force, which is not there in the circular cylinder. So this is because you have a flat facing surface of the cylinder. So the nature of this forcing is such that it starts to impact the motion of the cylinder, which means it feels more force or an apparent force, which was not there in the circular cylinder. Yeah. So in galloping, you have a negative feedback from the fluid. So instead of desynchronizing, it is actually increasing its amplitude. All right.
Correct. And is there some struggle between the high amplitude, high frequency vibration and high amplitude, low frequency vibration for the energy harvesting?
So whether it is high frequency or low frequency or high amplitude, low amplitude, I think the power includes everything. If you see the formulation of power, right, it includes both. So really, I think the question is good. If you see the power expression, what I put it in my slide, it has both components. So based on that, you actually get a complete larger power. So frequency is also important, and the displacement is also important.
Sir, then it is not necessary for power harvesting that which will work in lock-in region, or I mean any region, any frequency can give. That depends.
So by its very definition, if you see in lock-in, we have larger energy exchange between the fluid and the solid. So in a way, you are trying to harvest energy from the fluid. So lock-in itself is that condition that you have a maximum energy exchange. Any other region will not have that exchange at its highest level. So that's why the lock-in is actually the best indirectly to harvest the energy, because you are trying to take energy from the fluid and put it to some other use, isn't it? So that's why the lock-in is always the best to harvest the energy.
Actually, my confusion was that in lock-in, there is very high frequency, right?
No, it depends. It is not like that. So lock-in is when the fluid frequency locks to the cylinder natural frequency. So natural frequency of that system could be high or low, right? Depending on what mass you choose, depending on what flow speed you choose, depending on what spring stiffness you choose. So it could be either high or whatever value, not necessarily high. In a way, if you see the data I showed in login, it was always close to its natural frequency.
Any more question?
What immerse mounting method are you using in the or
I think I did not understand again. I think you are slightly far away. You have to come forward.
What immerse boundary method are you using in your simulation?
Okay, so it's a sharp interface immerse boundary method. I think yesterday lecture, if you have missed, we talked of two methods: continuous IB and the sharp IB. So this all things what I'm showing is the sharp interface, sharp immerse boundary method, which we have developed in our group. So we also use structure solver called Tahoe for open source structure dynamics to solve for it, and other cases we are using simple ODE based solver which is integrated into the fluid code for dissection or for this flow induced rotation. So those things are just simple in-house small solvers, but other cases like flexible plate, we have a dedicated structure solver, and the flow solver is based on sharp interface IB method.
Can we use continuous forcing?
Continuous also you can use. See, again, as we discussed yesterday, continuous is also easy to implement and use, but of course your accuracy will not be as strong as close to the boundary. So continuous, only problem is once you have very thin plates and all, then you have to refine a lot very close to the structure. You need more grid points, and then you need more adaptive refinement. So continuous also can be used, but of course you need to know how to increase its accuracy and what kind of grid resolution you should use to avoid the errors. Because as you see, we discussed yesterday, that the accuracy of our solution is on the order of grid size in continuous, while on the sharp interface is on the order of grid size square. So even if you refine in sharp, so the error reduces 4 times, but in continuous it will be just 2 times. In other words, continuous is first order accurate, sharp is second order accurate near the immerse boundary. All right. Any other questions?